Morning, everyone. Today, we will present our computer vision mini project on handwritten character recognition. Our goal is to build a system that can detect handwritten characters from an image and convert them into digital text. Our team members are Wu Mengzhou, Susan Ling, and Swantan Ling. This project combines image processing and deep learning techniques to recognize handwritten English alphabet characters. Handwritten recognition is a challenging task in computer vision. Unlike printed text, handwritten characters vary significantly between different people. There are several reasons why handwriting is difficult to recognize. First, variation in character size and orientation. Some characters may be large or small or titled or rotate. Second, different handwriting styles. For example, the letter A or G can appear in many different fonts depending on the writer. And the third one is stroke thickness variations. Different people write with different pen pressures and styles. And finally, noise from scanned or photographed image, which can make recognition even harder. Because of these issues, traditional OCR systems often struggle to correctly recognize handwritten text. Therefore, our project focuses on recognizing English alphabet characters from capital letter A to Z and small letter A to Z from handwritten images. Our project has four main objectives. First, it can detect handwritten characters from images. Second, segment each character using the image processing techniques individually. And the third one, classify the characters using a convolutional neural network, which is also known as CNN. And finally, we reconstruct the characters into words based on our predictions. By combining these steps, we aim to create a complete pipeline that converts handwritten images into digital text. We also would like to present about the reasons why we are choosing this approach. We choose to combine image processing and deep learning because they complement each other. Image processing techniques help us preparing the images and isolate characters from the background. It includes removing the noise and also improving the segmentation. After pre-processing, we use a convolutional neural network, which is also known as a deep learning model. CNNs are widely used for image recognition because they automatically learn important visual features such as edges, shapes, and patterns. This makes them very effective for character classification tasks. Therefore, I also would like to present about the overall system pipeline. Our entire system follows a 6-stage pipeline. First, the system takes an input handwritten image. Second, the image goes through image preprocessing, where the noise is reduced and the image is prepared for analysis. And for the third stage, the system performs character segmentation, which separates individual characters from the image. Fourth, each character is then normalized, meaning it is resized and standardized. And as a fifth stage, these normalized characters is passed into the CNN classifier, which predicts the corresponding letter. And finally, the predicted characters are combined to reconstruct the word. These pipelines allow us to process handwritten text step by step.
Hello, I'm Swantan and I'll explain the overall system pipeline and the flow of the system in details. The first step, the system pipeline starts by loading configuration setting include the file for the load characters. Next, the system loads the JSON label file, which connects the mapping between image file names and their text labels. After that, the system builds the dataset by segmenting characters from images and pairing them with their labels. The dataset then goes through data preprocessing, where images are normalized and labels are encoded. Next, the dataset is split into training and testing tests, and the end model is built and trained for 15 pouch. Finally, the training model is used to predict characters from images in the task folder, and the results are displayed. I'll explain step 2. The system opens the label JSON file and checks if it exists. If the file does not exist, the file not found error is raised. If it exists, the file is loaded using JSON loads, converting it into a dictionary that maps image file names to label. The system then prints the total number of labels and returns the label dictionary. In the step 3, characters are extracted from word images. The images first convert from visuals to grayscale, then Gaussian blur is applied to reduce noise. Next, also thresholding converts the image into binary form. Controls are detected to locate characters, and small controls are removed as noise. The bounding box are sorted from left to right, and each character is cropped. Finally, character's pattern resized to 28 into 28 pixels before being returned. In the step 4, the system looks through each image and label pair in the dataset. First, it checks whether the label contains only alone characters. If the image file exists, it is loaded and passed through the character segmentation function. If the number of segmented characters match the label length, the character image and labels are added to the dataset array X and Y. In the step 5, the image are converted into NumPy array with shape and 2828 pixel value are normalized by dividing by 250 feet, and the channel dimension is added to match CNN import format. For labels, label encoder convert characters into integers, and when hard encoding convert them into vectors for classification. And CNN model architecture, it takes 28 into 28 grayscale images simplified. It contains 2 convolution layers with rectifier linear unit activation, each followed by max filling for feature extraction. The output is then flattened and passed through a dense layer with 120 neurons. A drop-out layer helps reduce overfitting. Finally, a soft max output layer predicts the probability of each character's class. In the model training, the model is compiled using the atom optimizer, categorical cross entropy loss and accuracy metric. Training runs for 50 epochs. During each epoch, the models perform forward pass, calculate loss, and updates weight using bug propagation. Validation is performed using the test datasets to monitor loss and accuracy. Then, the dataset is divided using train test plates. 80% of the dataset used for training and 20% for testing using reliable model evaluation. For the prediction, a new image is loaded and segmented into character. Each character is normalized and reshaped before being passed into the CNN model. The model predicts the character class and label encoders converts back to the original character. Finally, operated characters are combined to produce the final predict one. Now I will explain the image preprocessing stage. Before we can detect characters, we must first clean and simplify the image. We use 3 main preprocessing techniques. The first step is grayscale conversion. This converts the image from RGB color to grayscale. This reduces image complexity while preserving the important structural information. The second step is Gaussian blur. Gaussian blur smooths the image and removes small noise or irregularity that may interfere with segmentation. The third step is auto thresholding. This technique automatically converts the grayscale image into a binary image where pixels became either black or white. This helps clarity separate the characters from the background. In the character segmentation, after preprocessing, we perform this step character segmentation. Segmentation means separating each individual character from the image. To achieve this, we use contour detection. Contour is a curve that represents the boundary of just the image. Once contours are detected, we draw a boundary box around each character. However, not every contour corresponds to valid character. Some contour may represent noise or smaller max. Therefore, we apply filtering conditions such as width must be greater than 8 pixels and height must be greater than 20 pixels. This contour helps remove unwanted contour, keep only valid characters. And then character normalization steps comes. After segmentation, each character must be standardized before being passed into the newer network. This process is called character normalization. There are 3 steps involved in this step. First, we add padding around the character to ensure that it's centered. Second, we place the character inside the square image frame that we resize the image to 28 by 28 pixel. This size is commonly used for character recognition and model and ensure that all the inputs of the neural networks have the same dimensions. Next, I will explain the CNN architecture used for the classification. The input layer receives a 28 by 28 grayscale image, then we apply the first convolution layer with 32 faders and a 3 by 3 corner. This layer extra visual features such as adjust and cuffs. After that, the max Boolean layer reduces the spatial size and keeps the most important features. Next comes the second convolution layer with 64 fader followed by another max Boolean layer. After feature extraction, the data is flattened into one-dimensional vector. This vector passes through a fully connected dense layer with 120 neurons. To prevent overfitting, we also apply dropout with a rate of 0.3. Finally, the upper layer uses soft max activation to classify the image into 52 classes, represent the uppercase and lowercase English letters. The model was trained using the following configurations. The dataset was divided into 80% for training and 20% for testing. We used the ADAM optimizer, which is widely used for deep learning due to its first convergence. The loss function used was categorical cross and trophy, which is suitable for modern classification problems. For training setting, number epochs 50, batch size 64. These parameters provide a good balance between training, time, and model performance. Thank you.
We conducted several experiments to determine the best configuration. We tested different factors including different number of approach, different segmentation threshold, using all character versus alphabet only, and padding and no paddings. After testing these variations, the best performing configuration was character like capital A to Z and small letter A to Z. Approach is like 50 and segmentation threshold are like width is greater than 8 pixel and height is greater than 20 pixel, and pattern is also enabled. These configurations give the best balance between accuracy and stability. For the model performance, our final model achieved the following results. Training accuracy was 94.89%, and validation accuracy was 79.72%. And our training loss was 0.1482, and validation loss was 1.7. So the difference between training and validation accuracy suggests some generalization challenges. Most errors occur due to segmentation mistake or visually similar characters. Here are some example of prediction from the system. So if we write Paris is beautiful, it was predicted as a PARGINGHEAUTFUL. And hello, if we type hello, it was predicted as LLELLO. And also my name is became MINENEIS. So these examples show that the system can organize many characters correctly, but they errors as they occur. And so most mistakes happen because a character are incorrectly segmented or visually similar. And there's several limitations in our current system. First is segmentation error. Sometimes characters are split incorrectly or merged together. Second is similar characters. So characters like I, L, and T look very similar and can confuse the model. So third is a class imbalance. Some letters such as Q, A, Z appear less frequently in the data set. Finally, word level error can occur when multi-level character prediction are incorrect. So To improve this system in the future, several improvement can made. First, segmentation can be improved using morphological operation, connected component analysis. Second, data augmentation techniques such as like rotation, scaling, noise addition can increase data set for diversity. And last, more advanced deep learning model like ResNet or AfficionNet could improve classification accuracy. Finally, we can implement word label correction methods such as like a spell checking or language model to improve the final reconstructed text. So this concludes our presentation on handwritten, like a character recognition using computer vision. Thank you very much for your attention. We will be happy to answer any question.
Here is our demonstration. This is the corridor desk.